Okay, awesome. So next up, we have Cameron Moy, who's going to tell us about Roulette, which is a language embedded in Racket for expressive, exact, and efficient discrete probabilistic programming. Take it away, Cameron.
Thank you. There's actually going to be a lot of similarities with the last talk, so thank you, Manny. This is work done with Jack, who is in the room, John, Brianna, and Stephen. We're all at Northeastern University. So why another discrete PPL? It really comes down to, for us, these three adjectives: expressive, exact, and efficient. So let me say a little bit about what those are. So first of all, for a probabilistic programming language of the sort we care about, we want it to be extremely expressive. So what does that mean? It means that programmers should be able to program in a very natural style. In other words, to be able to write programs as if they were using a conventional programming language with all of the features that you might want from that. So that includes higher order functions, mutable state, modules, but also might include some more unusual features like macros, say. So we would like that. That's the kind of most important aspect. But the other two are also important. One is that we're looking at exact inference. So the inference should give you deterministic and precisely correct results for all of your probabilistic queries. That's opposed to approximate inference, which is also very common. And we're also looking for efficient inference. So we would like it to be as fast as possible, and we would like to be able to scale to reasonably large programs. So we're not interested in just handling toy programs. We would like to be able to actually write large pieces of software and be able to perform inference. Okay, so we would like to be at the intersection of all of these three things. And so that's what I'm going to propose with some caveats, which I will get to at the end. Okay, so to motivate this a little bit more, let me give a concrete example. An example I'm going to give is of unreliable hardware. So suppose you're working at a company which is producing hardware that is going to go off into space and is going to be exposed to gamma radiation, for example. And there's going to be some probability of some errors. Maybe you perform an operation and it doesn't actually work correctly. So you would like to write a simulator for the scenario and run a program, say, through the simulator with a certain error rate. And you would like to see what's the distribution of results from that. Okay, so how would you like to write that? Well, if you're a functional programmer, you might like to write it like this. Here's an implementation of a simulator, and it's written in a very high order style. Every single command is a function that takes in a memory and gives you back another memory. Memory is just represented as lists of bit vectors. Since we've written it in higher style, for example, you can see sequencing takes in two functions and composes them and threads the memory in the standard way. But what's interesting here, of course, is what happens when you do assignment. And assignment is going to be one of the operations which can be potentially faulty. And we see here, you might miss it if you're just looking at the code as a whole. You might think it's a regular scheme or racket program. But there's actually a flip in here. So with some low probability, instead of actually assigning to a variable, we're going to just zero it out. Okay? So suppose we want to actually run this on an example. So this piece of code is not particularly important. It's just calculating triangular numbers, but it's using the abstractions that I've defined on the previous slide. And here I'm going to be calculating the fourth triangular number. Okay? So we would like to simulate this. Here's an example of when the error rate is 0. And we get the fourth triangular number with probability 1, which is 10. And let me actually just increase the error rate a little bit, and you'll see that now we get some probability mass on some of the other answers. And then, of course, if I increase the error rate, we're going to get more probability mass on the others. And if I increase it quite a lot, then you can see we get a lot of noise out. Okay? So we would like to be able to run programs like that. So how do you do that? So we have a discrete probabilistic programming language called Roulette. And it brings together two ideas, which kind of are existing in the literature, but turns out that they work really, really well together. And that's kind of the big idea of this paper. So I'm going to give a bit of background on both of them. So the first big idea is to execute programs using a symbolic evaluation. So this is kind of a variation on symbolic execution, which I'll go into in a moment. And by executing programs in that way, you get concrete values, which are guarded by Boolean formula. OK, so what do you do after you get that? You can then perform inference by using these Boolean formula to calculate probabilities. And like the previous talk, we're going to use knowledge compilation to do that in a scalable way. OK, so let me talk about these two ideas and give some background on that. So the first is symbolic evaluation. This idea, there's some concurrent work, but the main piece of inspiration for us is the Rosette programming language, which is where the name roulette comes from, which is a solver-aided host language inside of Racket for building DSLs which need solver-aided capabilities. And I should also like to say, if the one thing that you come out from this talk is that, oh, Rosette is cool and I should check it out, I actually would be perfectly happy with that. Rosette is amazing. It's very mature. There's lots and lots of tools that are built on top of Rosette. But I think it could be even more widely used. So if you've ever reached for Z3 bindings, I would encourage you to instead look at Rosette and see if it can help you out. But we're going to build critically on top of Rosette. So let me explain how Rosette executes a program. So Rosette augments Racket with a first-class notion of symbolic variables. So the first two lines here are defining two symbolic Booleans, which means they could either be true or false. We're going to leave it unspecified. And then the rest of the program can be basically a regular Racket program. So I have conditionals. So I'm saying if x0, 2, 3, and then similarly with y1. And then I'm going to add them together as if it's regular numbers. OK, so how do I want to execute this program? So I'm going to go line by line. So the first one is going to create a binding for x0. And on the right-hand side, we have this thing called a symbolic union, which is basically a list of pairs, where the first component of the pair is a guard, and the second component of the pair is a concrete value. So on the left-hand side, we have a formula, and that's a logical variable, x sub 0. And on the right-hand side, we have any kind of Racket value. So here, in this case, these are concrete Racket Booleans, true and false. OK, so I can do the exact same thing with x1 and get a very, very similar structure. And then what happens when I try to evaluate the right-hand side of the binding for y0? I have a conditional. And the conditional is going to be on this symbolic union, which could be either true and false. So what's going to happen is, like in traditional symbolic execution, we're going to have to explore both paths. So we're going to evaluate the true branch and the false branch. And then what's going to happen is we're going to merge those results together in order to get another symbolic union. Okay, so the binding for y0 is going to be this symbolic union, where we have the concrete values 2 and 3, which are guarded by those same logic variables. And very similarly for y1, we'll do the same. Okay, so then what happens when we get to some primitive operation like plus? Well, we're going to add the y0 and the y1 together. These things are symbolic quantities. They're symbolic unions, though. So we can't just apply addition ordinarily to them. So what Rosette also does is it lifts the operations of the language to work also over these symbolic unions. And in this case, what we can do is essentially take the Cartesian products, apply the primitive, the real addition to it, and then merge together those results into another symbolic union. So it looks like this much larger symbolic union here. And we have some of the Boolean formula. And you'll notice that we have a little bit of savings here, because there's actually 2 ways to add up to 6. So we have a Boolean formula that's a little larger for that particular result. OK. So in terms of symbolic execution, what is this really telling us? This is telling us all of the ways that you can get these results. So the left-hand side of symbolic union, the formulas, every model of that formula corresponds to some concrete execution where you've instantiated the x0 or x1 with some choice of a Boolean. So for the model x0 and x1, where we have assignments true and true, that leads to 2 and 3, which gives you 5. So if we go through the symbolic union and we look at all of the models, that summarizes all the possible concrete executions of the program. So we can do the same thing with 7. And then for 6, there's 2 ways to get 6. And we can see that reflected in the fact that the Boolean formula, the guard, has 2 models, where we have false and true and false. OK? So 2 of the main ideas of symbolic evaluation, and I've given a pretty simplified look with respect to that. There's a lot more ideas, so you can look at the Rosette paper for more of the details. But I think the 2 main ideas are, when you get to a conditional, you're going to execute both branches, and then you're going to merge the results into symbolic unions. And the second idea is then you lift operations of the language to work over those quantities. So let me compare this a little bit with some other techniques that you might be familiar with. So symbolic evaluation in lots of cases is able to avoid path explosion via this merging. So this is similar to in bounded model checking, where there's a merging that occurs to avoid path explosion. And then symbolic evaluation also avoids having to encode every single language construct that you have in terms of a formula. This is similar to symbolic execution. So you can inherit the semantics of the programming language instead of having to encode everything manually into some formula or symbolic representation. So in some sense, you can think of symbolic evaluation a la Rosette as combining the best of bounded model checking and symbolic execution. It's a kind of a hybrid of the 2. OK, so that's about symbolic evaluation. What has that got to do with inference? Well, I'm going to have basically the same program. And you can think of it almost the exact same way, except think of the symbolic variables being generated instead as now random variables. So instead of symbolic, define symbolic, we're just going to have flips. And you can think of running and evaluating this in exactly the same way. The only difference is going to be there's probabilities associated with these logic variables. So I'm going to run through each of the lines again. And it's going to be exactly the same, other than we're keeping track of probabilities. So the first one here is we have the same symbolic union as we have before. But then we have this W here, which is a weight map associating logic variables with their probability. So this is a global map that we're just going to keep track of, where here x0 is mapping to 0.4. And the same thing on the next line, except now we're updating this weight map to also have a mapping for x1, which is 0.7. And then we have the exact same symbolic union as we had before. OK, so you can think of evaluating the program Rosette style, except now we're going to keep track of this weight map. And now I have to do something with that weight map. And now this is where inference via knowledge compilation comes in. And as was mentioned before, a lot of the inspiration comes from the DICE programming language. But there's also some prior work that is inspired this work as well. OK, so how are we actually going to calculate the probabilities of the various results that we get at the end? And what we're going to do is we're going to do weighted model counting. So like I said before, every model of these guards corresponds to a concrete execution trace. Now what we're going to do is we're just going to weight each of those traces and then add them up. So in the first example, we have x0 and x1. And if we look at that weight map, well, we can calculate the probability of that particular concrete execution by just multiplying those 2 together. And we get the probability that 5 occurs. And very much similarly for 7, except now we're going to take 1 minus the probability associated with the logic variables. And then for 6, there's 2 models. And therefore, we're going to take the weights of both of those traces and then add them together to get the result for 6. But we said efficiency is really important. So how are we actually going to calculate these weighted model counts? knowledge compilation. So these guards are going to be represented by binary decision diagrams, and then binary decision diagrams admit an efficient weighted model counting algorithm. Now, you can't always, perhaps, efficiently compile to a BDD, but if you can get there, then you can do the weighted model counting very efficiently. OK, so then the final result is this probability distribution at the end. So you get your symbolic union, you calculate the weighted model counts from the BDDs, and then that gives you your answer. OK, so the main idea is to compile these Boolean formulas into BDDs and then perform the weighted model counting. But you have to use that auxiliary weight map in order to actually do that operation. And so what are the consequences of doing so? Well, the knowledge compilation bit gives you scalable inference for discrete PPLs. And then when you add that to symbolic evaluation, then you also get expressivity as a result, because the symbolic evaluator is doing the very hard work of converting a program with a lot of high-level language features into the summary of all possible executions, which you can then do the weighted model counts on efficiently. OK, so how expressive is expressive? I gave you the example in the beginning, but just to drive the point home, I implemented this slideshow in Hashlang Roulette. So that demo that you saw earlier where I was interacting with the error rate was actually running the roulette program. So you can see here, this is the language implementation that I talked about earlier. This is memory perturbing operations. And then here's the program that I was running. And then here's the GUI that actually renders that and performs the inference. And what's interesting here is that Rosette has interoperation with the host language Racket. So since Racket has slideshow capabilities, then we're able to just require in Racket slideshow capabilities and then just use the flip capability for the example. OK, so if it's expressive enough to write your PLDI slides, then it's pretty expressive, I think. OK, so I mentioned we're interested in the intersection of these things. So we think roulette is a good answer to that question of what exists in that space, with a few obvious caveats, which I will now go into. And there's perhaps more. You can see the paper for more caveats. But the two perhaps most important ones is that we're talking about discrete probability here and not continuous probability. There's potentially some interesting work combining symbolic evaluation and being able to do continuous random variables. But at the moment, roulette does not support that. And the other thing is that it's unclear from the current design naively how to accommodate some features like almost sure termination. So there are some limitations with naive symbolic evaluation, but combining it with other techniques, say, for example, laziness, you might be able to overcome some of these. So these are things for future work. Let me say a little bit about what else is in the paper. So we have two theoretical developments. One is a model of an idealized version of Rosette, which extends on existing work on the theory of Rosette. And in particular, extending it to handle things like mutation, which is important for, say, conditioning. That theoretical development is set up in a way which nicely generalizes to roulette and the correctness of roulette. So everything in the Rosette setting has a nice analog in the roulette setting to nicely generalize. So Jack and John did a lot of work getting that, so thank you. The other thing is we have some benchmarks comparing roulette to dice. And we see that it's relatively competitive with dice on most of the benchmarks. So the summary is really that you get a lot of additional expressivity, but you're not actually losing performance from that. And there's lots more fun stuff, so I encourage you to check that out if you're interested. The other thing that I'll say is, at least for me personally, I'm really interested in people trying this out and telling us about their experience and if they have ideas or applications. So I've tried to make it as easy to get as possible. So if you have Racket installed on your computer, there's a single command that you run in Bash that will get roulette and will get it running, I think. And there's also documentation online that covers the whole language that we've implemented so far. So please, if you're interested and have applications, try it out and come talk to Jack and me later if you're interested. Thanks.
Thanks for that great talk, Cameron. Let's take one question before lunch. I have. Go ahead, Frost.
For the nice talk. So from the expressive standpoint, it seems the large gains in expressiveness in Roulette are from more PL features, data structures, all that stuff, modules. But in terms of the statistical modeling, it's restricted to sort of these discrete distributions over a finite number of variables. Have you found cases where this increase of the sort of PL expressiveness enables you to write models which are finite and discrete, but other systems, in principle they should be able to, but it's just far too complicated or they're not ergonomic enough? And what are some examples of that?
Yeah, so that's a great question. I would say that one of the things is that you can develop much more quickly when you have a more expressive host language. So one of the examples that we have in the paper is we were able to take an existing implementation of a logic programming language in Scheme and just directly embed it in a Roulette program and have a probabilistic logic programming language out of that, albeit one that's very inefficient in certain ways. So I think from my perspective, having increased expressiveness just in the PL side of things and not perhaps in other features will allow you to write programs much more quickly and easily. And I think that's good for developers, hopefully.
Great. Okay, well, let's thank Cameron again and all of our speakers. Thanks for coming to the session. And now it's lunch.